A thing to keep in mind is that Carnot's engine is fictional. It's an ideal engine. It doesn't really exist. It has no friction. It has no other ways for it to lose energy other than doing work or energy going straight to the heatsink. And so for a real engine, the real efficiency is always going to be less than the Carnot efficiency. So it's always going to be less than 1 minus T low over T high. A simple example of a real engine is something called the Stirling. One common design of a Stirling engine looks like this. There's more than one way to set this up, but this is one class of Stirling engines. Here you've got a cold temperature sink, so this might be enclosed in ice or some cooling fluid, and this is a hot temperature source, so maybe there's some flame here from a candle or a gasoline fire, or solar panels or something like that. And they're connected by this shaft. These are pistons. There's gas trapped here and there's gas trapped here, but that gas is connected. It's one volume of gas really that moves between these two cylinders. In the first step of this cycle, what's happening is the gas is being heated by this Q from the external heat source. So flame heats up this gas. When you heat up gases, they expand, and so what we have here is an isothermal expansion. The crank turns, this shaft is connected to this crank, and the crank turns because the gas expands. The other thing that's happening as this crank turns is that this shaft gets pulled on, which means this piston gets pulled on, and that forces gas to go into the cold cylinder. What happens next is the fluid cools fairly quickly, isochorically, so without much volume change, as the momentum in the crank forces the fluid into the cold cylinder. So energy is being lost through heat very rapidly to ice or a cooling fluid or something like that as the crank continues to turn. And that pushes more of the hot fluid over into the cold cylinder where it cools down. This is all happening when the volume doesn't change very much because this piston is near the top of its motion. It starts to move upward much more slowly than it had in the past and comes nearly to a stop. Then the crank continues to turn. As the crank turns, that pushes the piston down in the cold cylinder and moves the cold fluid back into the hot cylinder. And then the process starts over again because the momentum of the piston starts to expand the hot cylinder. Q begins to go in from the hot source. Heat flows in from the hot source. That expands this gas, and it starts to push this piston outward and force gas into the cold chamber. So the process goes over and over again, repeats itself, as long as there's a temperature difference between the hot and cold cylinders. So just keep going on and on. Constant flow of energy in at the hot source, out at the cold sink, and in the meantime work is done. This is the Stirling cycle. It's different than the Carnot ideal cycle, and so it's less efficient. One of the things that's different, the primary thing that's different, is you have isotherms here, you have isotherms here, but you have an isochoric expansion and an isochoric compression. That's not perfect. Stirling cycles are not ideal, so their efficiency is less than that of the Carnot cycle. There are other heat engines that exist out there. Some of them are quite common, some of them are not as common in our modern world. Reciprocating steam piston engines used to be really common. In the 1800s, that's how most power is produced. It's an external combustion engine, so you make steam by boiling it in a place other than where the cylinder is.
One practical application of a heat engine is a reciprocating piston steam engine. This is an external combustion engine. An external combustion engine has the combustion, the fire, happening outside the engine. By contrast, an internal combustion engine has the combustion happening inside the working fluid. The combustion that heats the steam can come from any source. Fossil fuels are commonly used, have been in the past, coal and oil. You could use wood. That's how a lot of steam trains were run in the early days of this country. And then you could also use any renewable source. You can heat it up with nuclear power as well. The basic idea, you've got a boiler that's got some water in it, and you burn something, fossil fuels, coal, whatever it is, and you produce a bunch of heat. That heat goes into the boiler and boils the water. And then that steam, now water vapor, runs into the engine. The engine extracts work from it, and that goes into the surroundings to drive your train or generate power or whatever. And then the fluid cools off, loses heat energy, and ends up back in the boiler as liquid water. The actual engine itself is a cylinder. It's like this classic gas expansion cylinders that we've seen in a lot of these ideal examples. Piston's connected to a crank, and the crank collects the work as rotational kinetic energy. So there's a crankshaft down here, and this will spin around. That can be hooked to a generator or to the wheels of your train or whatever you want. If you look close up at the cylinder, there's a valve. There are two valves, actually. One allows gas out and one allows gas in. So the steam coming in, carrying with it some heat from the boiler, enters through this valve when it's open, and that causes the gas to expand. The piston is pushed down, making the cylinder larger, until it reaches bottom dead center of the rotation, and then it starts to turn around. This gas is now cooled off considerably, and as the motion continues around, the valve on the exhaust side opens up, and the valve on the hot side closes. The motion of the piston pushes the used up steam out, and energy is exhausted to the atmosphere with the steam. And this process repeats itself over and over again. And so you get this circular power output that you can hook up to some device. Here's what the cycle looks like. As the steam pushes the piston out, work is done and the gas cools off. This is near adiabatic. Not exactly, but pretty close to adiabatic. Then, once the piston starts pushing the steam out, the pressure is constant because the valve is open to the exhaust, and so you see a decrease in volume and also a decrease in temperature during this change. There's a loss of energy to the surroundings with the exhaust. Then the compressor, or some kind of a mechanical pump, increases the pressure as it pumps the steam back to the boiler. That's going to be near adiabatic as well because it's happening rapidly. And then the gas is heated up and it expands under constant pressure inside the boiler, so that's an isobaric. So we have adiabatic, isobaric, adiabatic, isobaric in the steam PV diagram. This is actually more realistic. This is called the Rankine cycle. And if you look at this thing closely, you notice that the isotherms have these goofy shifts in them. Like here's T1, goes down to here, jumps up here, comes back down, and then you can follow T1 out the other side. T2, same thing. Pops up here, and then comes out there. And the reason for that is because you have some phase changes going on there. When it changes from liquid to gas, that messes with the pressure-volume diagram. The efficiency of these devices is about 10% typically if you have them exhaust directly to the atmosphere. But you can improve the efficiency by several means. One thing you can do is you can increase the efficiency by having a compressor pump mechanically condense the gas before it goes back into the boiler. Another thing you can do is take the exhaust gas from one cylinder and run that into another cylinder, and it runs at lower pressure. You can see the pistons are getting bigger and bigger, and they have to do that because the gas is providing lower pressure, so for the same force you need a bigger area, and then that exhaust gas can be put into another piston that's even bigger and operates at even lower pressure, and then eventually it gets exhausted back to the boiler. That kind of multiple usage can increase the efficiency up to about 25% or so. And then what you can do in addition is you can collect the waste heat as this fluid's going back to the boiler and use it for other things like heat your power plant, or maybe make another fluid that boils at a lower temperature than water boil and run a different generator. And so you can get the efficiency up to about 85 or 90%. Historically, steam engines were used for lots of things. The first real heat engines that were practical were steam engines, and they ran trains, they ran power plants, they ran mills of all kinds, industrial mills. But when oil became really cheap and the internal combustion engine was invented, internal combustion engines are way lighter because you don't have to have these giant boilers carried around. That makes it much more practical to do an IC engine, and so they've kind of fallen out of favor. But they still are used to generate power and for a few other purposes as well.
Steam turbine engines don't have a reciprocating piston. They just spin around and around and around, and as gas is forced over some blades, almost like blowing on a pinwheel.
Here we're watching a part of a steam turbine, and you can see that some of the rotors are spinning and some of them aren't. The ones that are spinning are actually called rotors. They're like big pinwheels is what they are. The ones that aren't are stators. They just stay in place. The stators direct the flow of the steam so that it hits the rotors at just the right angle to cause them to move, like that. What we've got here is a steam turbine stack. We have a lot of stators and rotors here, and those stators and rotors get larger as we move away from where the steam enters at the center. That's because the farther the steam goes, the less force it has, the more it's been used to turn rotors. And so with less force, to make the same torque on the same shaft, you need a bigger lever arm, because torque is force times lever arm. So the rotors get bigger and bigger, have a bigger radius, bigger lever arm as you go farther down the stack. That provides a constant output of torque. Here we see the steam washing down the rotor and back up a larger stack on the other side, and then the output shaft is going to drive some kind of a generator.
Reciprocating internal combustion engines are the ones that are most common today. Our cars and trucks are all powered by these things primarily. Gasoline engines.
Here we see a cutaway view of an internal combustion engine. There are multiple cylinders here. It's a complicated engine. There are a lot of complicated parts, but the two moving pistons that we see here are the most important things there. Here we see a close-up view of one of the pistons going up and down, now two of the pistons going up and down, and here's a list of the stages of internal combustion engine function: intake, compression, ignition, power, and exhaust. Each of those stages are play important roles. We see two valves here. The valve on the right is called the intake valve. That opens up to let a mixture of gasoline and air go into the cylinder. That happens as the piston moves downward, increasing the volume of the cylinder. Gasoline and air mixture rush into the cylinder until it reaches near the bottom of the stroke, when that valve snaps shut. With the valve snapped shut, we now see with this larger view that the cylinder is getting smaller as the piston moves up, driven by the momentum of the crankshaft down below, and compresses the gases into a smaller space. It makes their temperature higher, and it makes it easier to ignite. That's the next stage. The spark plug that's located at the top of the cylinder ignites all these gases, and they burn very rapidly. That causes them to expand. That pushes the piston back down, increasing the volume of the cylinder. Next thing that happens is the exhaust valve on the left opens up, and the exhaust gases, the products of the combustion, are pushed out of the cylinder as it gets smaller when the piston moves up. Let's watch the whole cycle in action again. Here's intake. Air and gas go in. Intake valve shuts. The mixture is compressed. The temperature rises. Spark plug ignites it. The power stroke occurs. The rapid combustion drives the crankshaft around again. Exhaust valve opens, and as the cylinder gets small by the piston being pushed up, the exhaust gases leave.
Diesel engines combust a different way. They combust diesel fuel. These require a spark. These don't require a spark. Compression gets it hot enough just to light it off that way. And then there's another type of engine that's less common today, and that's a rotary internal combustion engine. Sometimes these are called Wankel engines.
The rotary engine is based on this very clever idea that if you offset, if you make it not go on a centered circle, this tri-lobed little triangular sort of looking rotor, it sweeps out this shape. And someone decided to take advantage of this and take advantage of this fact that it makes different size spaces. You can see this volume of gas getting squished down into a smaller space and then opening up into a larger space again. And then as the rotor continues to move around, the space that the air is squished into gets smaller again, and then the cycle repeats itself. So here's what we have going on. As it sweeps past the intake port, it takes air in, compresses it, spark causes it to expand again, and then it sweeps past the exhaust port, and then it gets pushed out. And that cycle just continues. And so instead of having one power stroke every 2 cycles like you do in a reciprocating piston engine, you have 3 power strokes in every cycle. And there was only one drawback, and that is that the seals that cause these little patches of air to stay in place would wear out very quickly.
Those were used in a few sports cars in the 1980s and 90s, but are not commonly used anymore. And then there are jet engines. There are ramjet engines that just use forward motion to compress gas and oxygen into a chamber, and then it's ignited. And then turbojet engines use the motion of the engine itself to compress, so you don't have to be moving fast to make a turbojet work.
This is a simplified picture of a jet engine, a turbojet engine. What we're looking at right now is the compression zone. This is the combustion zone, and then behind that we have the turbine, and then the exhaust will come after that. How the thing basically works is gas is forced, air is forced into the jet. The compressor makes it smaller and smaller, forces it into a smaller space because it's cone-shaped. The air then gets very hot and is moving very fast, and then in this zone up here you can see there's actually combustion. Fuel gets squirted in there and it ignites. That makes it even hotter and faster moving. The gas then moves past this turbine, which is like a pinwheel, and that spins really fast, driving the compressor, and then the rest of the energy is used to just drive very hot gas out the back end. By Newton's second law of motion, if gas, matter, is moving backwards, then the jet has to move forward.
All of these kinds of engines and more exist out there, and the ones that I've listed here, steam turbine, steam reciprocating piston, internal combustion engines, and these two jet engines, you should learn about these things. Go out on the internet and find sources that will tell you how each of these types of engines work, and be prepared to explain them.